Oh, okay, so. Okay, so I got the Darwin data in. The first problem is, of course, it's a paired design. So let's analyze it the way Darwin should have. Try to check it and see how else. I never thought to do that. There's the cross is first and the solve is second. So we want the differences. Let's call them these, I guess. Or maybe dip. So it's 1 minus 2, right? Bigger is better. So there's differences, and most of them are positive. I guess there's 2 negative ones. Then you just have to do the sign right 4 box on it. And again, I don't want to do this by hand. I would have to take the absolute values and rank them. But that's a lot of work. I have 15 data points. So it would depend on the software you're using, right? If you were on Minitab, you would just do W test on the differences, right? And this could be one sample on RGLN. We're on R at the moment, so we'll just use low box dot test. Right? And although I would want a one-sided one, but then you have to look at that help file or whatever. But you know what you're after, and you really will be on the upside. There's no way you're going to be on the downside with data like that. So you can just do a 2-sided test and cut the p-value too. Okay. So if you're lazy, yeah, today. So weird. I remember. So it's highly significant, right? One side would be 0.02. If you did 2 sides, so the height is what? It's about 3.13 more inches, or whatever Darwin measured in crossover style. Too confident that it doesn't contain 0. Any questions on that?
So that there is a 2-sided test?
Yeah, right.
Okay, so the 1-sided would be like half that, right?
Right, 0.02. And the other thing I ran an experiment on is the experiments if you this data. But the other one, it looks sort of random. It doesn't look like it's linear at all. Right? You probably didn't have to do a pairing. You was going to do the design again. They're not correlated. And you have a couple out. Okay. So now you need experiments, and again, we depend on the software we have. We're at get this one. do want ties, regression ties, so. Yeah, here it is, four tests, XY method. The correlation is minus 0.334. Trying to get you from that. It's not significant. Looks like they do a t-test, okay, the one you talked about. You could use a simple one. Okay, and it's also, any questions on that? So again, that calculated, and you have that constant down here, remember? And there's a t-test where you can just use. Okay, I forget what a T is. A T is. Yeah, it's formula 6.3. Any questions on that? Probably that correlation is caused by the outliers. See, what you can do with plot? Suppose you want to, we could turn this into a regression problem. How do I? Any questions on the Darwin data then?
The rank of xi, is it when you find out the rank, do you put x and y together?
No.
It's just x and y.
Right, separate rankings, right? This is correlation in separate rankings. Okay, any other questions? So, well, I guess we could look at it as a regression problem. I got the plot the wrong way. Any other questions on that? Okay, I put some more notes out on regression, and let's go over through those. And then we'll have a quiz. think the notes, where we are, we've done these squares, right? We've done the work box now. So, again, there's 3 ways to do it, right? You do Minitab, RTLM, or you need to install RKit, and you also have to install Parametric. Nicole, did that time work?
I didn't try it with that yet.
You need Parametric and
Quant rank and fit.
but again, you don't, if you're not using R, you don't have to. You can use R, DGR, you can use RTLM. It's almost like it's best to know that you can do it, right? And you feel comfortable. One set of graduate students, I know she was always lost on because she couldn't get a post-norm solution. I said, well, I try to convince her that you don't do these squares like that either. These squares involves referring a huge matrix, and yet P is large, number of matrices is large. And actually, the best algorithms of these squares never invert that matrix anyways. Does it like a QR decomposition on a singular value? So, I once went to a lecture who said before the age of the computer, the biggest non-pattern matrix which was ever inverted was a 20 by 20. It's just, we could fit thousands of variables. That means you'd have to invert thousands by thousands. Okay, so let's call Y. Suppose you want to project cross, that would be in terms of X would be actually solve. I mean, it's kind of a dumb example. We have leverage values. That's not let's see what else we have. Why don't we just do the baseball? It's certainly simple to understand. Yeah, we'll just their type. The way.
There we go, there's the baseball. See it's in here. So this is the height of the baseball players. It's very easy to understand.
So we talked about fitting, so let's go ahead and fit. And the first thing would be, on an inference would be, we have the estimate. Let's talk a little bit about the standard error and then the confidence. Okay. So the estimate of slope is 5.7, so for every inch in height, you expect a baseball player, or you predict, okay, I shouldn't say expect, because now we're with the data, you predict a baseball player to increase weight by 5.7 pounds. So this has a lot of meaning. This, of course, is that there's the intercept has no meaning whatsoever, right? So that's for a baseball player who is 0 to 10 inches tall, you predict his weight to be minus 220 pounds. So you don't have any data near 0, so you can't use it. So you have to just ignore this. Okay? So there's the estimate in the table of coefficients. The thing beside it is the standard error, and from that you can make a confidence interval. The confidence interval is just going to be the standard error times a z or a t critical value. You might as well use t. Won't really matter much here. N is 59. Okay. Or you can test the hypotheses that slope is 0 using this t ratio, which is nothing more than the estimate divided by the standard error. So let's do the confidence interval first. So let's, how about the error and confidence interval? So let's use a t critical value. We could look it up and just type it in. In fact, why not just do that so I don't make things, let's just use a z critical value. 1.6, which you could look up the t or you could do it with r. Okay. And then put in the standard error. So there's the error in my confidence interval is about 1.5. So here's the lower bound. It's going to be the estimate, which is 5.71. It's minus the error, right? And then my upper bound will be 5.7. So here's my confidence interval. It goes from 4.2 pounds to about 7.2 pounds per inch. So you have a degree of uncertainty in the data. If you look back at the data, that shouldn't shock you, okay? It is sort of it's not that compact, right? Not that tight. We could also do an overlay. That's easy to do with, we just need to fit a value. So just add lines of the plot. I had to pre-sort the X.
I should have used circles, huh? There's
Any question on a conference symbol? Okay, so let's talk about a couple more conference symbols. We could use T or Z, okay, let's see. Standard error, right? That's what we talked about. Oh, then you can do a test.
Your hand looks pretty scary. Your hand looks pretty scary today, big, really big.
That's the T ratio that comes out in that table in the third column. You can just use that as your test statistic. That'd be approximately a level off the test. But this is equivalent. This is always, no, always. I shouldn't say that. Usually it's two sides. This is equivalent to the confidence level. It's just a simple algebra manipulation to show that an equivalent test is to reject H9. 0 is not even C. So you can test that just like you do with, E squared. Okay, there's a couple other confidence symbols we should talk about. You're always thinking about predicting. And the first is actually we estimate a mean with the expected value. And some particular value that is. Now, of course, if you substitute that into the linear model, it's just this, right? It's the intercept plus beta 1 times x5. So certainly your estimate is just beta hat 0 plus beta hat 1 times x. Right? And, in the example we're talking about, maybe you want to estimate what the expected weight for a baseball player who is, I don't know, 6'4" or something. So an example, say that's 76 inches. Just be one half so that would be the intercept. course. That's what we talked about that. Okay? So you just have to compute that. And if it's a point in the data set, I don't know, do we have a 76? Yeah, actually the third from the last, right, is a 76. So we could just do y hat again. 205. So for a baseball player who is 6'4", I predicted his weight to be 206 pounds. Okay, well then we need a constant symbol for that, right? That's just an estimate, right? And the constant symbol is of this form. Standard error is this time n. Now that's not a nice thing to compute, right? You're going to have a computer do that for you, for sure. Actually, I don't think I'll do this. I'm thinking. So we could talk about how to compute here. But the thing to notice is, this is x naught minus x bar squared. Okay, this is the only place that x naught enters into the whole formula. But it's a very important point, okay? That's a square, it's always non-negative except when x naught is equal to x bar. In that case, that will be 0, and that term will vanish. Now you're just adding on something that's non-negative. So that's the shortest confidence interval, and it really makes sense because it says you have the most precision for this estimate is right in the center of the data. Okay? And if you're far from the center of the data, you're going to pay a hefty price for prediction. Okay? It's going to get much wider. Now, it doesn't get wide enough when you go beyond the data, right? What you have here is like a gravity. So, here's your data. So, here's x bar. And so, if you apply this confidence interval, actually, not perfect. See, right in the middle of the data, you have a short interval relative to what you have at the limit. Now, if you go beyond the range of the data, it increases, but it doesn't increase fast enough. You've got to be very careful when you get outside the range of the data. Okay? The model is only good where you have data. You don't know what's going to happen. This is a dumb example, but it's hard to see what will happen. In this case, you really would want to go on beyond the data and think anything. But often, X could be time, and then you do want to predict the next time unit for the next few time units, right? And you can do the prediction, and you can write down the error of prediction or this expectation. I have to see. I don't think there's any. There's a command called attributes to tell you which attribute. Okay, there's a related problem, and I keep saying in prediction, actually, I think we estimated this expected value here, but we did it with the predicted value, that's why I keep saying it. But the second thing is actually a prediction itself. The problem is, the prediction's the same. But you're doing something different, and a good example is that, like the GPA. Suppose you're trying to predict GPAs in terms of ACT score. And so the first thing we just did was we got the expected GPA, say for all students who scored 28 on their ACTs. This was here, you just want to, Johnny scores 28. You predict his GPA. So you're asking two different things. Here you're actually predicting the random variable. So if you think of normal, your prediction is going to end up looking with like a couple standard errors. That would be your interval. So the standard error is predicted. This is called a predicted. Looks actually like this. I take that tau hat inside, and I pick up the sigma hat squared. And next one over this. Now, what's that sigma hat squared? That's just going to be a robust estimate of sigma squared. We need to talk about some of this. You see, it's like you're adding what? Plus or minus 2 sigma, even more. Okay? Even more because you have done estimation. So this confidence interval, this is a predictive interval. It'll be much wider than the first one. Okay, so that gives us confidence intervals. Still a few things we have to do. So there's a couple more things in regression, and then we can, we want to do multiple regression. That shouldn't take long at all, okay? Everything's set for multiple regression. That thing we minimize, we just add extra terms. So this thing we've been working with is generalized. So we'll talk about it. We have to talk about a few more things in regression. We have to do multiple regression, and then we can start doing like all days overs, things like that. Okay? So you ready for the quiz?
I said no.
You don't have to.